Good evening, everybody. A very warm welcome to all our participants, colleagues, and panelists joining us today for this third session of the Fusion Energy Masterclass. We are quite delighted to see such strong and continued participation from all of you. Your engagement reflects the growing interest and urgency surrounding fusion energy as a transformative clean energy solution. It is of my particular pleasure to welcome our distinguished speaker for today's session, Professor Ambrogio Fasoli from École Polytechnique Fédérale de Lausanne, or EPFL in Switzerland. Professor Fasoli brings an exceptional combination of scientific depth, leadership experience, and global perspective to this series. It is also my pleasure to welcome all the panelists present with us today, Dr. Ranjay Sharan, Professor Vijit Sen, Dr. 𝘍𝘶𝘴𝘵, and also our project director, Dr. 𝘚𝘂𝘀𝑃. Before we begin, let me just briefly recap the journey so far. In session one, Dr. 𝘍𝘶𝘴𝘵 introduced the fundamentals of fusion and magnetic confinement, covering tokamak physics, exhaust heat handling, liquid metal divertors, and emerging role of high temperature superconductors. In session two, Professor Vijit Sen examined plasma physics foundations, India's fusion program, highlighting India's role in ITER, and outlining strategic pathways involving technology development, leapfrogging approaches, and policy direction. Today's session builds naturally on these foundations and takes us a step closer to the core of fusion energy. We will explore why fusion remains a compelling energy option, revisit its fundamentals with particular emphasis on burning plasma. To guide us through this complex landscape, we are truly honored to have Professor Fasoli with us. Professor Fasoli is currently the Provost and Vice President of Academic Affairs at EPFL. Until the end of 2024, he served as the Program Manager, CEO of the EUROfusion, where he played a central role in coordinating Europe's fusion research strategy and its contribution to ITER. He has previously served as the Director of the Swiss Plasma Center, from 2015 to 2024, and as the Editor-in-Chief of the IAEA Journal of Nuclear Fusion between 2014 and 2020. Professor Fasoli studied physics at the University of Milan and earned his doctorate from EPFL. He conducted his research work on the jet tokamak in the UK and later joined MIT as a professor of physics, where he worked from 1997 to 2001. He's a fellow of the American Physical Society and a member of Academia dei Lincei, Academia Europa, and the Swiss Academy of Arts and Science. His illustrious career uniquely spans frontline plasma physics research, large-scale program leadership, and academic governance at the highest possible level. Professor Fasoli, it's a true privilege to have you with us today. We are very grateful that you have taken the time to share your insight to our community. The floor is now yours.
Thank you very much for this wonderful introduction. I am delighted to be with you today. Let me share my slide. I will certainly have some repetition with respect to what my colleagues and friends have already lectured about. But as I was joking a few minutes ago with them, repeating things doesn't always hurt, and particularly when considered a bit different from what you're used to or a bit difficult. So I will have some fundamental elements, also some elements of motivation, and then I will discuss a little bit what the burning plasma specifically is, but also the vision that at least until last year I had for fusion in Europe as an example of one way to move forward along our path. So I start with a nice, let's say, movie here showing what happens inside the sun, our star, where we know that fusion energy is generated by the reaction that put together protons to form helium nuclei. And then, of course, those reactions release energy, which takes a long time to come to the surface of the sun and then short time to come to us. Now, we do not have that long time. Neither do we have the mass to bring it all together and keep the high pressure and temperature like the stars and the sun do. So we have to do something slightly different. The idea, again, is opposed to breaking big nuclei to go down in the curve of stability of the nuclei, as we see here, and that is fission, is to do the opposite. Why going down in a curve reduces energy? Because you go towards a state of increased stability, and when you increase stability, you don't need that energy to hold the nucleus together anymore. You can release it, and this is what fusion does, going down from left to right. In other words, going from very light nuclei to slightly less light, but still very light, like helium. So the going down from left to right, as you can see here in this visualization, of course, is steeper than going down from right to left, which means that the density of energy you extract from your fuel is even significantly higher than the one you extract by providing and by operating nuclear fission. And that's one of the main advantages of fusion. Now, as I mentioned, we cannot afford using the slow fusion reactions that are used in the sun, in the core of the sun, the proton chain that is, but we do have ideas for faster fusion reactions, and that fastest of all is the one between deuterium and tritium. And by fastest, I mean the one which has the reactivity or the probability of happening, which is the highest at temperatures that are not extremely high. Now, not extremely high is still a relative way of saying. You can see here the cross-section for the different fusion reactions that we consider. The blue one is, as I say, the easiest of all. That's the deuterium and tritium, and it has a decent value, I should say that way, when you start having tens millions of degrees in terms of temperature. Of course, it's difficult enough to do DT. So at the moment, in my opinion, we can consider basically operating the future reactors in DT, and of course there are other efforts around the world that may say, okay, well, we want reactions without neutrons, so let's look at other possibilities. But I think it's difficult enough that we have to concentrate on the one that the easiest of all in these terms that I mentioned. In other words, in the cross-section versus temperature curve, so the highest of all. Nevertheless, we need to be 100, 150 millions of degrees, at which temperature, of course, matter, as you know, in solid or liquid or even gas form does not exist. It only exists in this plasma state, which is a soup of completely dissociated atoms and molecules of basically positive nuclei on one side and negative electrons on the other side that are together in this soup, which exhibit collective effects and which has also the dynamical behaviors that are very interesting to study, but very difficult to control. And that's part of the challenge that we have in front of us. We cannot do without plasma physics, because at the temperature at which fusion happens, the matter is in the form of plasma. And of course, doing plasma physics is something that's very interesting, not only for fusion, because plasmas are actually characterizing pretty much most of the universe, at least the universe we know of. We don't know what the dark matter or dark energy are, so we cannot say much about that. But the universe that we know of is mostly made by plasma. So I say often to my friends in astrophysics, doing astrophysics without plasma physics is like doing oceanography without knowing what water is. And unfortunately, that is not a statement that is always taken too seriously, because you can sometimes have astrophysicists that in fact ignore plasma physics. So that's a little point from our fusion physicists saying that actually we are much more general than some people pretend we are. So if you do fusion, which I hope you will do, you can also have impact on many other areas of physics. Let's go back to our favorite reaction, which is D and T reacting together to form an unstable nucleus, which decays immediately into a helium nucleus that is an alpha particle. That's a charged particle, it's 3.5 MeV. It's a hell of a lot of energy, which will remain, hopefully, at least that's what we are aiming at, in the plasma to give energy back to the plasma. That's what we call the self-heating on the plasma. The second outcome of this reaction is the neutron at even higher energy, 14.1 MeV. So that's much higher than the typical energy of neutrons in fission reactors. That neutron has two jobs. One is to carry the heat out, which will make electricity. And second, and that's key, is to reproduce part of the fuel, and that part that doesn't exist is what needs to be reproduced. That is tritium. And how does it reproduce it? Well, it produces it using a nuclear reaction with lithium, namely lithium-6, that will be put in a blanket surrounding our little star, so that you can make a tritium nucleus again, which you will re-inject in your plasma, and a helium nucleus, which will also be captured in the system. And by the way, that also brings even more energy eventually. So tritium is made in situ around our reactor, and deuterium is brought in because deuterium is present pretty much everywhere around our globe, for example, in the seawater in very high percentages. So there are absolutely no issue about the deuterium as a fuel for fusion. It is virtually unlimited. The reaction with the lithium to produce tritium is very easy and very simple to write on a board or to put on a slide, but as we will see, in practice, to make that regeneration work is not so trivial. Now, why do we fight so much, all of us together in the panel here, and all of our colleagues since 60 or 70 years for fusion? Because the potential of fusion is gigantic. As I said, you have a gigantic energy density. Just to give you a rough example, I am from the city of Milan in Italy, where there will be the inauguration of the Olympic Games in about a week, about 10 days. That will be happening in a stadium which contains 85,000 people. It's a football stadium. Now, why do I talk about the stadium? Because for the town of Milan, for the city of Milan, which is for Indian standards not that huge, but it's let's say 1.5 million people, for 1 year of energy, if you burn fossil fuels, which unfortunately is done today, you need to fill that stadium up all the way to the top with coal. Okay, that means about 25,000 trains that come for 1 year of energy. The day we will use fusion energy, not only do we not need to fill a big football stadium with carbon, but we will actually bring the fuel in an amount that is transportable in a truck of a car, or even in something that you can pull with a bicycle. So this is really the extent that makes fusion such a potential game changer for energy business. So de facto, the fuel is practically inexhaustible and of course, well distributed geographically, because the deuterium, as I said, is present in water, in seawater. You don't have any greenhouse gas emission. There's no combustion, of course, and you don't have any long-lived radioactive wastes. The fusion reaction itself doesn't produce radioactive waste. Of course, the neutron activates the structure depending on the materials that you use for your own structures, but that is not, even with the present materials, for a long time, and it's not something you have to dispose of on a regular basis. We cannot lose control in the sense of exponentiating the reactivity, such as it can happen in fission. And we have, at any given time, because of this very, very high energy density, a very small quantity of fuel in the reactor. And in the approach that we favor in our community, in Europe at least, that is magnetic approach, basically there are no links with the weapons program, which is also, I think, a big plus. Obviously, it's an energy that you can turn on and off when you need, and it's not subject to weather or other kinds of sources of intermittency. Now, you can say, okay, why do we need fusion, given that we are embarking so well and so significantly into the renewables that we are deploying, wind energy, solar energy, and of course, hydro? Well, I give you an example that is a very clear example from Europe. First of all, I remind you that this is the 2024 data. 2025 is not very different, that we are still basically counting on natural gas, oil, and coal. You can see the percentage of other things is still really small, but that I don't need to convince you. But I really wanted to give you an example that comes from Germany. Germany is a country that has invested very significantly in renewables, and it's very nice to know that. Very nice that they've done that. Trouble is that they have installed, let's say in 2018, 2019, they've invested 350 billion euros, which is more than 350 billion American dollars. They've invested in wind and solar in over 2 years. So this is the data that I could find over 2 years. And they say, okay, we install about 150 gigawatt. Now, this is more than the need of power on average for the country. And I have this data from the last summer. You see the electricity consumption. This is the sort of magenta curve up and down. Of course, that's day and night. And you have the actual power, produced by renewables out of an installed capacity of 150 gigawatt. And yellow is sun, and blue is wind. There's blue onshore, which is a little bit less dark, and blue offshore, which is darker. And there's also very pale blue, which is hydro, which is more or less constant. Germany doesn't have proportionally huge hydro. We are more fortunate in Switzerland because of the Alps, of course. Now you can see under the curve of electricity consumption, there's a lot of white. What does that mean? That means that for that white, Germany burned. What did it burn? Fossil fuels. As a consequence, despite an investment of hundreds of billions, there was no reduction in CO2 emission. So you need base load. This gray stuff is what actually is produced by conventional fossil fuels. So you need a base load, even in one of the most, should I say, virtuous country in terms of investments on renewables. And that is why we need fusion. So I like to use that example because it's a quantitative underlying of the difficulty with the renewables. I will concentrate on magnetic confinement. So you have certainly heard from my colleagues that you need a certain value of the product between how much plasma you can confine, and that is in terms of density, and how much time you confine the energy of this plasma for. And that product is around 10 to the 20 per cubic meter times seconds. And you can do it on Earth in two ways. You can do it with inertial confinement. Basically, you give up on trying to confine. You just allow the mass to fly out because of its inertia. So you will not take zero time to fly out, obviously. But you need then to ramp up your density to very large values. And this is by a complicated ablation and compressions procedure. Or you can say, okay, but I can choose to work with very low densities. 10 to the 20 per cubic meter is about 100,000 times less dense than the air we breathe. But in that case, I have to hold the energy for macroscopic time, that is over the second. And that's magnetic confinement. Now, you can have magnetic fields that it can try and trap particles. But as soon as you trying to make a close geometry for those magnetic fields, you see that you have a problem of confinement if you don't do something special. So on the top, you see that if you don't do something special, the particles gyrate around, and because of fundamentals of plasma physics, which I'm sure you have already learned, I'm just reminding you this, the particles drift one way or the other, depending on the sign of their charge. And once you separate charges of different signs, you of course create an electric field, and that again takes everybody out. So that is really no good. So the solution is to have helical field lines, which are represented on the bottom, where you can see the particle is trying to drift a little bit to the one side in the bottom, but then as soon as it does that, it has to come back to the other side because of the helicity of the magnetic field lines, and so it drifts the other way around. So all in all, the drift is on average removed, and then the particle can be nicely confined in the absence of other interactions in this cage made of magnetic field. And of course, you have two ways to make this cage. One way to make this cage is by making a combination of a toroidal field by external field coils, toroidal field coils. So the coils that are around here in blue make a toroidal field in one direction. In order to make it helical, what you do? Well, in the tokamak case, there's this clever idea that you drive a current inductively in the plasma, which is the secondary of a transformer. And that current, of course, make by your right-hand rule, a field that goes in a poloidal way, which combined with the toroidal field makes a helical set of field lines. And that's exactly what you need to make a very effective cage. And so far, this is the most effective cage we have made on Earth. And that's, of course, the constant of the tokamak. The other option is to make this helicity by coils that are themselves complex in their shape and therefore in the form of what we call a stellarator. In this case, you do not need the plasma current, so you have the advantage that you don't need to drive it inductively. Therefore, you can be intrinsically steady state and you don't have the instabilities associated with that current. So this is the idea. Now, why is it that we have deployed and we are deploying so much effort in science and simulations and in the validation of the simulations? Well, because the plasma is a complex matter. It's very nonlinear. It's dominated by collective effects, and is very multi-scale. So you have the charged particles that are sources of electromagnetic fields because they move. So they create charge and current density, but in turn, they, of course, are victims of the magnetic and electric field they produce. And so this is intrinsically self-consistent system, which is difficult to simulate. And you have to go from this time scale and spatial scale of the motion of individual electrons, for example, around the field lines. That's fraction of a nanosecond typically, and the fraction of a millimeter, to the scale of a very large reactor, which is minutes and many meters. So that multi-scale feature makes it very difficult to simulate. It's also by construction a complex geometry, and the geometry which has intrinsic anisotropies. Their directions are not equivalent. And also you have very, very large gradients. Large gradients meaning that the edge of your system, you can have a very cold matter. In fact, just outside you have a very, very cold magnets, as I'm sure Dr. 𝘠𝘵𝘶 has explained to you. And inside your plasma, you have to have 150 million degrees. So you have gradients that are very large. Sometimes we say it's the largest of the universe. We have no idea why we say that, but it sounds nice. But indeed, they're very large. And that means when you have large gradients of pressure, large gradients of temperature, large gradients of even electrical current, in the case of tokamaks, you have what we call free thermodynamic potential. So you have the potential of driving instability. And those instabilities are very nonlinearly coupled, and they give rise to turbulence and turbulent dynamics. Very difficult to simulate, very difficult to control. Sometimes you have nice self-organizing events, such as in this little movie that I'm showing, where you have the turbulence that generates flows that all of a sudden are organized or seem organized. These flows are nice. Why are they nice? Because they provide insulation for thermal transport. Sometimes they're not nice because they provide bubbles, they provide eruptions of plasma, even from the plasma surface. So we need to control all of this. And even to simulate is complicated. It's also multi-physics because you have complex constitutive relations of the matter itself, as I say, complex dynamics, but you have the pure plasma in the core, which is completely ionized, so no atoms, no atomic physics. But of course, as you move to the core, the edge, you do have atoms, you do have atomic physics, you have molecules, you have impurities, you have a system which is not at thermodynamic equilibrium. It's also emitting radiation of all different kinds. And eventually, at the end of its path, it touches the metal walls. And so there is a plasma-solid interaction as well. So it's really complex multi-physics. I have a little movie of our own tokamak, a little minute of publicity, because this is a very nice visualization we've done with the experimental museologist of our university. She has taken actual orbits of the particles inside our tokamak, the actual geometry of a tokamak, and she has made this visualization. Unfortunately, we don't have the glasses, but it's 3D. And this tells you the complex dynamics that happens inside a tokamak. And this is a tokamak that doesn't produce energy. It's an experimental tokamak at Lausanne in my university. So you see the orbits are complicated. You can identify different kinds of orbits, different kinds of particles, and different kinds of interactions. So that's what we need to study. We need to study that at different scales as well, from the individual particles to collective instabilities to collective features that we need to tame and control from outside. I'll let you hear this. I don't know if you hear the noise. Do you hear the noise?
The sound in the video, you mean?
the sound is on purpose a noise. And what is that? That is the noise of the best plasma in a tokamak so far in the world.
Okay.
That is the noise of the jet records discharge, where we obtain the fusion energy record. I say we because it was of course, a European project, JET, in UK, but also with a lot of collaboration from overseas.
Professor,
And
can I request you to play it once again so that we can hear it?
I will do it. I will do it. Let me just say that again. I was just saying that, of course, it's a European project, but it's also strongly collaborate. There were strong collaboration with the US, India, and other countries. So I played once more.
Unfortunately, we don't hear it, but we see it.
Oh, I'm sure Rakesh has explained to you why you see the light at the bottom and not in the core. In the core, you don't see light because there's no atoms, so there's no atomic transition. The bottom is this complicated divertor thing that you have learned about from Rakesh. Now, why was that a record shot? Because it was the little experiment of a few seconds, which produces 69 megajoule. 69 megajoule is the amount of energy that is the largest of everything we have tried in a world so far. It was obtained at the end of 2023. JET was decommissioned at the end of last year. The year before. That amount of energy was obtained with about 0.2 milligrams of deuterium and tritium fuel, 0.2 milligrams, as opposed to a few kilos of conventional fuel that would have taken to create that amount of energy. And we beat our own record. We beat by a large factor our own record obtained in the late 90s, when I was actually physically myself at JET. And we beat the record by quite a factor. And like in sports and like in Olympic Games that we will see next week, I think it's very rare to beat a record by a factor of 2 or 3, right? Normally you just file a little bit of time or the distance you jump and so on. So this was very important. And even more important was that it was done in conditions that are similar to what we anticipate for reactors. And by that, I mean in a path that's reasonably long, and especially with materials surrounding the plasma that are relevant for a reactor. So for us, this is a further confirmation that we are actually on the way to doing it. And by doing it, I mean to not only having a scientific experiment, but also to extract energy at some point from our plasma. I just had to mention for correctness that, of course, there were very interesting results from inertial fusion as well. There was this prowess shown in experiments in which locally there was almost a factor of 2 between the energy injected in inertial fusion, so lasers coming, impinging on this little capsule of gold in which there is a pellet of deuterium and tritium, and the efficiency of this implosion and explosion were so good that there was about a factor of 2 in gaining the energy. That's a factor of 2 in gaining the energy with respect to the energy that was injected in that particular single event, and of course, and in that particular location. It's not the energy that was taken from the grid to generate the laser light. Obviously, that's another factor, almost 200, if I'm not mistaken, to take into account. So that means in terms of production energy, we're not that close, but in terms of demonstrating that you can extract more energy out of your plasma than you put in, this was a fantastic result. Now, going back to magnetic fusion, this is the chart that shows our progress, and that underlines how fast we've gone, despite the impression that we give to sometimes the public and politicians, because it is the most difficult thing we ever done. So it is difficult. That's just a sheer piece of truth. But it's nice to observe that to heat the plasma, it was not the big deal. Of course, everything is relative. But what is really the key point is that we have to increase the product of the plasma density, the confinement time, and the temperature. And this is the challenge that we're facing. We are at the last bit of this journey. And the last bit of this journey is to go to a region where diffusion power divided by input power exceeds at least 5. And we have been up to almost 1. In reality experiment, we'll be up to 0.7 in the jet experiments. This is the experiments in which I took personally part at the end of the 90s, but not more than 1. And why do we need to go to more than 5, at least more than 5? Because that is the regime where we can start thinking of having gains that are compatible with what you need for a power plant. But why 5? Why do I mention the number of 5? Because when Q equals to 5, you have as much self-heating of the plasma as you can inject from outside. And so that's the threshold at which the plasma starts, as we call it in our community, burning. I remind you the fundamentals here. So you have the plasma heating from alphas, the plasma heating from external sources that you inject from outside. And of course, that has those two terms fight the losses, basically define the confinement time. Now you can assume steady state, you can assume on the left, you have 0. My point is that the fusion gain is basically 5 times the alpha power divided by the input power. So when this ratio is 1, you start burning, and therefore you have to have a Q of 5. When Q is 5 or more, you enter the regime of burning plasma. And that's the regime that's unexplored. We must be in that regime for a power plant, and therefore we must explore it. We must know how to control it, how to identify the issues that are in there that are not present in present devices. So this is a plot in which you have the self-heating fraction as a function of this Q factor. As you can see, Q promises to be in the region of Q of 10. For a demonstration reactor or more, you need taking into account the engineering efficiency to be of order rather 20 or 30 or like that in terms of this capital Q. When Q goes to infinity, we call it ignition, but we have recognized that we don't need to go to ignition. We've been so far a little bit below in magnetic fusion, a little bit below break even, as I said, about 0.7 with jet. So we have a way to go. And that is exactly what we're building in ITER and what other experiments are coming about. What's going on in a burning plasma that is a bit different intrinsically? I have this picture, which is a complicated picture. And the main point of this picture is that it is complicated, in fact. And why do I say that? Because I want to underline that in a burning plasma, everything is dominated by alpha heating, okay? Alpha heating is produced by the fusion reactions. Alpha heating influences the instabilities because it changes the gradients, because it changes the way the plasma behaves in the core. Instabilities affect the transport of energy and momentum and particles. The transport, of course, gives rise to fluxes. The fluxes change the profiles of density, energy, and even electric field and temperature, and those profiles influence, of course, the fusion productivity, the fusion reactivity, and so on and so forth. So there are self-consistent loops here, which we do not have in present devices because we're not dominated by alpha heating. In present devices, everything is dominated by what we heat, what we launch from outside. From outside, what can we do? We can heat, of course, some, and we will have to heat some unless we are getting ignition, which we probably never be. We have to inject momentum. We have to drive the current. We have most likely to try and control actively instabilities that happen in the plasma at the edge or in the core. We, of course, have to drive the current inductively. We have to fuel. We have to pump. We have to control the shape. We have maybe to control and mitigate the disruptions. Those are the controls that we have from outside. But the plasma dynamics in the core is going to be partly self-organized. So this is something we need to understand. And this is, if you like, the plain English version of that graph, underline that we are in a nuclear environment, and therefore there's also a question about treatment, retention, dust, and breathing, which I mentioned before. We also in a parameter range that's different in terms of basically just say simply the ratio of the size of the orbit and the size of the device. And then you can imagine like thinking about the ratio of the size of the waves versus the size of the ocean. That is a different regime in terms of turbulence. And again, will be dominated by a large isotropic population of alphas. So what we have is this thermal plasma, which has a very non-thermal component, which is the most important one we have in a sense, because that's the one that carries the energy that needs to be self-heating the plasma or re-injected in the plasma. And these are examples of orbits that we have in our tokamak. And these orbits are complicated because they are large and because they have a very non-trivial geometry. We also very high density, but also large temperature, which implies we have very low collision frequency for charged particles. So to reach and sustain the burgeoning plasma regime, we need to confine very well these fast or suprathermal ions. Those are the most precious things we have in our plasma. How do we make sure we understand the least and possibly minimize this loss mechanism? Well, we have to study them one by one, because even if you wanted to, we would be able to study them all together in the present plasmas because they're not yet in a burning regime. So we can look at what the magnetic field imperfections do, what kind of instability we can have, low or or high frequency, and if the turbulence does something to these fast ions. I just skip on the other three elements. I want to mention one element. It's also because it was my research, especially when I was at JET. There is one interaction in the plasma that is specifically concerning these alpha particles or these suprathermal particles, and I like to highlight that to you among these elements that may make us lose or redistribute fast ions. And that is the resonant interaction with alpha waves. So once more, we have external power in, we have the DNT that hopefully fuse. 20% of the energy of the reaction should be kept in the plasma by the alpha particles, 80% goes out. But this 20% is crucial to keep the plasma hot. Now, it happens that the alpha particles are born with an energy that, let's look here in terms of velocity, that is just above, that corresponds to a velocity that is just above the velocity of a crucial wave in the plasma, which is called alpha wave. So remember this. I will come back to this in a second. So that means they can resonate with this wave. Now, the ions are hot, they fuse, produce the alphas. The alphas have to slow down. Nature has made us a little bit mad about what we need to do for fusion, because they made us overcome a lot of difficulties. One of these difficulties, it really is intrinsic to nature, is that when the particles are so fast, like the alphas that are born from fusion reactions, they give the energy to the electrons and not to the ions. Unfortunately, because what we want is the ions that react, of course. So that means there's a macroscopic time for them to slow down and give the energy to the electrons, which in turn give the energy to the ions. So that macroscopic time is so-called the slowing down time for the alphas, is a time over which they may be lost. And if they're lost, we are in trouble. And they can be lost if they resonantly interact with a wave. And as I said, this is called alpha wave, the most important one. The alpha wave is the wave that propagates along the field lines. And along the field lines, you can have a transverse perturbation that is related to the perturbation in the magnetic field, and it propagating along. Why is it propagating? Because it's a combination of the tension of the field lines as if they were guitar strings, and of course the inertia of the plasma that's glued to the field lines in a hot plasma case. So a combination of inertia of the plasma and tension gives rise to this propagation of alpha waves at this quite high phase velocity. Now, the alphas have an even higher velocity when they're born, and so they are bound to encounter this resonance. It means they are very good surfers. They are very good surfers because they catch the wave perfectly. And if you catch the wave perfectly, you can get energy for the wave. Well, you can also give energy to the wave, but in the surfing analogy, of course, you would need zillions and zillions of surfers to give energy to a wave. But you do the opposite. You rather take energy from the wave. In the case of alpha particles, there are so many alphas that you can do that. But you can also, if you give energy to the wave, drive the wave unstable, and in turn being kicked out by the wave. So we need to study when and how this happens, how we can control that. This sounds very maybe theoretical or physics-based. And then you can also say, yeah, but the alpha wave on the guitar string that is basically the field line, they are present in infinity plasma. What about in a toroidal tokamak, in a complex geometry? Well, they're present there as well. And I will spare you the details how they translate into eigenmodes or special modes of the plasma, but they do. They are there, but the nature is the same. And they have been observed. They've been observed. This is an old plot from the lab of my friends here, and it was shown in the experiment in Princeton that there were waves that were propagating with the exact phase velocity that would be the one associated with the Feng wave. So here they are. They are there. Not only they are there in those, let's say, primitive measurements, but they're there also in the reconstruction of their structure. If you have a theoretical simulation that tells you exactly how beautiful this structure is, this is the alpha waves in this tokamak geometry, and then you say, well, okay, but the geometry in the tokamak is one thing, but there's turbulence, all sort of events, impurity, and so on. Is it real? Yes, absolutely so. This is a beam emission spectroscopy reconstruction of the measurement of the mode, which actually can be superposed to the theoretical reconstruction or the theoretical calculation, and you cannot find any difference. So it's something that we observe very well. It's very interesting to see how successful we can be in our reproduction of the plasma waves inside such a complex geometry. And so we measured directly that this instability happened. Do they have any effect? Yes. And this was compiled by one of the leaders, actually, the Princeton lab, Rich Horlock. As soon as you have the waves that are large enough, but large enough doesn't mean that much, but still large enough, then you have a fraction of the particles that are lost. When you lose a fraction of the particles, then the question is, how big a fraction can I afford? Think about ITER, 500 megawatt of fusion power. That means 50 megawatts in the alpha particle. How much of a fraction can you lose of 50 megawatt? Not much more than 5%, because they're not spread very uniformly. So it means you have to have a few percent and not more at the most of alphas that are lost. Otherwise, you're in trouble, not only because of fusion reactivity, but also because of the damage you make to the walls. And look here in this compilation, you have 1% losses when you have a mode amplitude of 10 to the minus 7 compared to the magnetic field. That's apparently a very small mode amplitude, but actually it's already enough to give 1% of losses. So we need to really make sure that we don't have a mode that's more than 10 to the minus 7 or so, which is not an easy thing to do. So that's why we still intensely study these waves and how to get rid of them or how to limit their growth in terms of nonlinear evolution. So that is one chapter of burning plasma physics that is still active, and I think is very interesting to see how we can confirm the predictions or not confirm the prediction in the future experiment. Future experiments, which of course will culminate, at least from let's say the mainstream point of view in ITER, which will be the integrated proof of the scientific and technological feasibility of fusion, because for the first time, it will obtain a Q of more than 10 in an environment, in a scenario, in a machine that is of relevance for future reactors. This is an international treaty, and nowadays we are very grateful to the international treaties we have, because we can work all together with the partners that are represented by flags here. Europe is the main partner because it pays almost half, and the other partners contribute 9% each. Of course, ITER is in France, so that also justifies why I say Europe is one of the main the main partner. And you have United States, Russia, South Korea, Japan, China, of course, India. As you know, ITER is being assembled. As you know, there's been a revisitation of the baseline, and I'm sure others have discussed this. We have a little bit of a delay. For magnetic energy will be in 2036, and DT operation in 2039. Now, of course, we are subject to criticism, and that's correct, for delays, for overspending. But if you have been or will be to ITER, you will see how amazingly difficult this project is, and the scale at which you have to do operations and installation and assembly and test is just unprecedented. This is, in my opinion, one of the most difficult things mankind has ever done, especially, I would say, for peaceful purposes. So it is just difficult, and whoever will try alternative routes, sooner or later will be faced to similar difficulty. Of course, having learned from what ITER has been doing and what is been doing, will be doing, you will be able to do things faster and more efficiently. But nevertheless, it's important to have this first really and unique facility from which, again, we learn day by day, not necessarily waiting for the ultimate experiments for the burning plasma. And as you know, ITER construction is going on, has been going on, and is still going on all over the world, which is a vehicle of, let's say, I would say peace. And you know how much we need that. Now I go to a little bit more European-specific vision. What do we have to do after ITER? Now, the vision keeps changing. So this is the vision that I was pushing myself in the EUROfusion consortium. You can call it in different ways, but we do need, in my opinion, one device that will demonstrate, after ITER will have demonstrated the scientific feasibility, that will demonstrate the performance, the integration, and the availability of key technologies. With a self-sufficient fuel cycle, in other words, to really demonstrate that we can run a blanket generated tritium and a net electricity output of the order of a few hundred megawatt with pulse length of the order of 2 hours. This is something we did discuss with the facilities, energy facilities, and we think this is one of the constraints we need to comply with. Are we ready to build demo? As of today, there are still gaps to be addressed. Of course, we need to go in parallel in different ways. One crucial gap is the blanket technologies. One thing, as I said already more or less 3 times, I think, is to write the lithium-6 reaction on the board. One thing is to actually have a blanket that absorbs the neutron. He has to, of course, first multiply them, slow them down, make them react with lithium to produce tritium, and screen the rest of the plant. And so these 4 tasks are not easy to do. They have to do it in a reliable way. They have to cope with very strong heat fluxes. They have to cope with a neutron flux, of course, and they have to be also subject to engineering constraints for a plant. We need to optimize the materials that we have, both the plasma-facing materials, but even perhaps more importantly, the structural materials, because of the effects of neutrons, the transmutation reaction the neutrons impose, and as well as, of course, the effect of the neutron knocking out atoms from their place in the lattice. And those 2 effects are very difficult to simulate because of the time scales and spatial scales involved, and once more, which are very, very diverse, even more than in plasmas, and also very difficult to simulate experimentally and to test experimentally because we don't have high energy neutron fluxes of significance to really test the materials. And this is why we need to develop facilities that do that. Divertor performance, exhaust, and extraction of power. I don't have to comment, but I'm sure Rajesh has explained to you how that is crucial and still has open questions. I will mention integrated plasma scenarios because you have to not run an experiment. You have to run a routine operation that goes from the birth to the death of every single plasma, every single discharge, which starts maybe a few minutes, but nevertheless has to start and stop without instabilities, without disruptions, without affecting the plasma-facing components, and so on, and without too many variations in terms of the power production either, because that will produce fatigue and that would also be very difficult to manage. We need to demonstrate the intrinsic advantages of fusion in terms of safety and waste, and we have not done that yet. And we also need, and this is something that a priori one doesn't think about, if we are just a fusion physicist, we need to do all of this using remote maintenance at pretty much all levels, and this is requiring a quite significant R&D effort before we're ready. As I mentioned, the gap that worries me the most, perhaps, is the one in the blanket. I just mentioned a couple of options that we have. We can use water-cooled lead lithium. So water is the fluid that will carry the heat out. You need the lead to multiply and screen the neutrons. You need, of course, lithium. But just to give you a flavor for the complexity of the engineering design, I put pictures of what's being developed in Europe here. There are concepts that are trying desperately to optimize the fraction of tritium that we produce over what we over the number of reactions we have in the core, and also to minimize the reprocessing time is an essential element to make a fusion economy work or not. We have an alternative concept which is called 𝘕𝘂𝗶𝗵𝗵𝗵 bed, in which you have pebbles that contain beryllium and titanium and so on, and then of course there will be another complex system there to evacuate the heat, in this case by helium, and neither of them seem completely satisfactory. So you need to maybe try to combine the concepts and see what you can do to have a functioning concept. That is to say, that is a crucial point. Divertor performance I don't mention because I'm sure you have discussed this with Rajesh. I just mentioned one point of a gap concerning to the plasma scenarios, as we call it. In other words, how to control the plasma from beginning to the end. You can have some kinds of instabilities generated by maybe a little impurity, may generated by unpredicted event that are called disruptions. These are instabilities which lead to a dramatic end of the plasma. It's not a dramatic event for safety of personnel or anything, but it's a problem for the machine. You have a loss of the plasma thermal content, and then the loss of the plasma current, and these happen very quickly. And once you have that, you still have a little bit of electric field that keeps accelerating the electrons around. And when the electrons are accelerating in the absence of plasma, or in the absence of a very dense plasma, they basically can be accelerated all the way to relativistic energies, because there's nobody to collide with, and the collisions become less and less efficient. So that is a problem, because when they become very, very fast, of course, they go to the wall. Can we do something about it? Well, we could try all of a sudden inject a bunch of mini, let's say, pebbles in a plasma, or pellets, as we call them, so that you can all of a sudden create a cold and dense plasma in the core that will provide some collisions for your electrons to slow down. This has to be done very fast. It has to be demonstrated to be compatible with the uses of machine afterwards, and so on and so forth, because we don't want this event to stop us for 10 years. And this is something still we need to do R&D on. This is an example of how we inject those, we call shattered pellets in jet. And that is an example in which the European program was dedicated to demonstrating the technology was specifically required for ITER. And this seemed to have worked, and as a consequence, ITER has decided to have several of these injectors for coping with the potential disruptions. The metals is another issue. You need to cope with a huge heat load to begin with. And just to give you a flavor, what kind of heat loads are we talking about? We're talking about tens, let's say, of order 10 megawatts per square meter. I can think of a turbine of a jumbo jet, or a nuclear fission reactor, or a satellite re-entering the atmosphere. You have thermal loads of the order of 1 megawatt per square meter. The only thermal load I can think of that's larger is the one created in the rocket engines when the engine is launched. But that launch, before you go outside the atmosphere, doesn't last very long. It lasts, I think, a couple of minutes, and that's about 8 times more. What we need to cope with is this 10 megawatts per square meter for decades, and that's a completely different game. And to look at what happens in the materials, it's very difficult, because the time scales, as I said before, and the length scales are from femtoseconds to tens of years in terms of time, and from atomic scale to cathedral scale in terms of space. Very difficult to do it. Can we have a machine that provides experimental tests? Yes, we can, and that's what we're developing in Europe, so-called 𝘕𝘂𝘶 machine, to produce a spectrum of neutrons that's not too different from the one produced by fusion reactions, so that you can test materials. You have a beam of deuterons that are accelerated onto a liquid lithium mini cascade, and those generate neutrons that go and impact your specimens. Trouble is, the specimens have to be small, because the volume of irradiation is small, and you still need to extrapolate what happens in a cathedral once you have understood what happens in a, let's say, small volume of half a liter and small specimens. So my point in this discussion, and sorry, this doesn't work, doesn't really matter, is that you need to address these challenges in an integrated way. When I'm asked what's the real missing element in fusion, it's not a single piece of physics, it's not a single piece of engineering, it's the fact of putting all of these things together. This integrated way is what ITER is already doing, and anybody who has to view fusion has to integrate this. Integrated means integration between physics and technology, integration between all the physics elements at once, integration between all the technology elements, but also integration between the different approaches and schools and labs. And that is something we have, at least in Europe, done for quite a long while. It's one of the, I should say, politically incorrectly, one of the things that in Europe has worked the best, the integration in science technology in fusion, in addition to high energy physics. We have worked together with our international partners, of course, to actually run all of this program. How do we accelerate? Well, we have to go and address these gaps. We have to do in parallel. We cannot wait the end of ITER. We have to increase efforts in simulations and use of artificial intelligence. We have to streamline the regulatory framework for fusion. In Europe, is extremely complicated because we have 27 plus countries, and many of them have completely different framework. And of course, makes the situation very complicated, and most of them are very restrictive. The only one that's not restrictive is not really in Europe, and that's UK. We, of course, have to use mutually beneficial collaborations, and that's something we're moving on as fast as we can move to things in Europe towards public-private partnership. The only way to go to NEMO is with the involvement of industry. But one point I like to make, and in the context of this discussion today, is crucial. We need to develop and retain workforce. All of this, and to some extent, it's reassuring as a human being. All of this is based on human beings. Fusion is driven by institutions and human beings. They have to be there with a wide spectrum of competencies, and they have to be there and collaborating together. You need young scientists, engineers, operators. These are the lifeblood of R&D and industrial development. Regardless of whether you are in the private or public sector, the private sector has to take people from our university, from our schools. And this is the bottleneck that is actually the most unavoidable of all, in my opinion. So that's why this is so important. So a way forward, in my view, a European view, is to parallelize things between science and technology, having ad hoc facilities that address these issues, and the ad hoc facility that integrate all of these things is ITER. But we don't need to wait for the end of ITER to start the next step, which is demo, or whatever you want to call it, because we can exploit lessons learned from ITER at all steps. And that's how we will go forward. Thank you very much for your attention.
Thank you. Thank you very much, Professor Fasoli, for that exceptionally illuminating presentation. I think it has given all of us a deep and nuanced understanding of the challenges on the path to make fusion a reality. So we'll now move on to the questions, and I'll read them.
I stopped sharing it, or I can see you better.
Yeah. And to our esteemed panel members, if you have questions in mind, just feel free to interrupt me or stop me between two questions, and please feel free to ask them as you at your will. So one of the question, I think you gave a very good update about the ITER tokamak. One of the question is like a comparison between the ITER and the Germany's W7 accelerator. Which concept you think will demonstrate commercial viability first? And a follow-up question is, what are the major material challenges for tokamaks and accelerators in your mind?
I think the tokamak line is, we say, one generation ahead. It doesn't mean that the accelerator is not promising. So in other words, we have had JET, well, of course, in the past FTR with tritium. We have demonstrated fusion power, silicon fusion power. We have demonstrated the confinement of the fast particles. The results from W7X are fantastic, and they are really telling us we have to speed up in our development on the next step for accelerator. So in my opinion, we need to go in parallel. In my opinion, we need to have the stellarator device that work with tritium that proves that we are able to go to the next step. If we want to go as of today, that's my personal opinion, okay, to the demonstration reactor as fast as possible, not the commercial reactor, but the demonstration reactor first, in my opinion, it better be a tokamak. It doesn't mean that the first power plant will not be a stellarator, but I think we are more ready, if I can say so, for a demonstration plant with a tokamak concept than with a stellarator. I also underline that many of the issues are completely agnostic of whether or not we have tokamak or stellarator. When we speak of the blanket, of course, the details are different, but the fundamentals are very much the same. And by fundamentals, I don't mean just the reaction, but I mean also the structure of the blanket and so on. The question of material is also very similar. The question of robotics is very similar. So some of the most severe gaps that we need to address, most important gaps, are common, and that's why we need to go in parallel. In terms of the materials, I'm not perhaps the most qualified person here, even in the panel, to address the question. But for me, now, as you know, we go to tungsten. There are several open aspects for tungsten, as in terms of the tungsten fuzz that's produced on the surface, in terms of to what extent we can really avoid that any significant amount of tungsten goes back in the plasma because of high Z material irradiating like crazy when it goes back in the plasma. But I would say the most severe, in my opinion, issue is the one of structural materials. We still have to demonstrate low activation materials that can cope with this fusion neutrons. And therefore, for me, and I hope you would also join the effort at some point. For me, it is very crucial to go as fast as possible to a facility that will irradiate materials with neutrons that have a spectrum that's similar to the one of the DT neutrons. So the showstopper for me is not having a device that produces neutron with the same energy.
Okay, thank you. The next question is, if you had to rank where the most engineering efforts or where engineering efforts buys the most improvement, let's say magnetic field quality or active control of magnetohydrodynamics or turbulence reduction, where would you put the next dollar and why?
I will not answer this question on purpose because of what I said before. I'm saying this a bit tongue-in-cheek, because for me, the point is not a single point. The point is integration. Okay. Because again, I like sports. One thing is to make a world record in 100 meters or high jump or the marathon, and that's individual sports. But we're not here for individual sports. We're here for decathlon, and it's the combination of different sports that counts. And that's why sometimes we hear people that have claims that are not realistic, not because individually they're not realistic or they don't know what they're talking about, but because they're not realistic in an integrated way. We have to combine the performance of the core with the performance of the edge. We have to combine the performance of the materials with the performance of the diverter. We have to combine the performance of the coil with the blanket and so on. So for me, the key point is the integration of the elements.
Okay. Thank you. So the other question is, what do you see as the greatest challenge for fusion energy, whether it's achieving reliable generation of 14.3 megaelectron-volt neutrons or developing material capabilities of withstanding long-term exposure to such high-energy neutron radiation?
Again, I could answer in the same way, but I don't want to repeat too much myself. So again, the key question is to do things at the same together, so that is integration. But I would say I think we have made enormous progress in the control of the plasma and in assessing the internal physics. The difficulty, if I had to say what would be the main difficulty now, would be more on taming what happens at the edge and interface with the surfaces.
Okay. There is the next question, which says that small modular reactors are a hot topic nowadays in fission community. Do you see any fusion counterpart of SMRs?
It's a very interesting question. if you look at the fundamentals of fusion, it's not easy to go very small if you think of your tritium generation. And that's why I'm sometimes a bit angry at some colleagues that, or pretending colleagues that say we can make tabletop tokamaks or producing fusion energy. Yes, perhaps, but you cannot produce tritium. If you don't produce tritium, there's no way out. So if you look at the cross sections for the process that I mentioned before, so multiplication, slowing down, production of tritium, and screening, you end up with a blanket that's at least of order 1 meter thick. And then you have a problem of the volume of the plasma that burns. And then you have the problem of the surface over which the power is deposited. So very difficult to imagine that you can go very small. And I think it's therefore even not very honest to actually say that you can go very small, because it's obviously easy to say, well, the smaller, the less expensive, the smaller, the quicker. And it doesn't work that well in fusion. Of course, we can do more compact than we have done so far. We can certainly optimize all of this, but the blanket can maybe be 0.7 meter, maybe 0.69, 0.68. It will never be a few centimeters, for example.
So we have a question from one of our esteemed panelists. The question is, would you like to share your views on the rapid growth and aggressive projections coming on from the private initiatives in fusion? Some, as we know, are pursuing the tokamak path with high temperature magnets.
Sure. I think it's a fantastic thing. There's so much investment, so much interest in fusion from private, which means we are really getting there. It's true that we shouldn't put all the initiatives in the same basket. There are some initiatives that are fantastic, so overcritical in terms of the mass and impact they can have, and some others that are undercritical, even though they have good ideas, and yet some others that have actually not good ideas. So we have to distinguish these things. We care. The approach with high temperature superconductor is very interesting, not because of the temperature so much, but because of the high field that you can produce. Therefore, you can make things a little bit more compact. Now, I say a little bit on purpose, because as I was saying before, if you make them very, very compact, then you have a real problem of number of megawatt per square meter. And very difficult to go around that. Nevertheless, to make it somewhat more compact is important. And those initiatives that do that, having a critical mass in terms of competence, people, which at the end of the day are the most important asset, and financial support, those are doing very well. The different parts of the world can have different models. I'm not saying that that, for example, Europe should have the same model as US or India or Japan or China. US is more going to the private initiatives, maybe allow the market to dominate. The approach in Europe, I don't think we're ready for that yet. Also, we don't have this kind of venture capitalist, but I think a combination of the two things is absolutely necessary. We will never create a demo reactor, of course, even less a power plant, if we don't basically have an industry taking the lead and working in partnership with us at the beginning, at least.
Okay, thank you, Professor. We crossed the 1 hour mark, so I'd just like to ask how much time you can afford, because there are few questions.
I'm fine as long as you're fine for at least for another 10 minutes or so. Yeah, no problem.
Okay, so I'll ask a few more that's in the Q&A box. So can you please elaborate on capturing the heat while generating tritium fuel in blanket? Because while all fusion companies are currently focusing on plasma stability, there is less clarity on the power conversion and the stability of the blanket. So your take.
So the heat is captured by the fluid that we use to cool the blanket. In the two components I mentioned before, very quickly, I admit, one fluid was water, very simple, and the other one was helium. Then say you capture heat with water, then you have a conventional cycle, thermodynamic cycle outside that will transform the heat into electricity. And that, of course, is intrinsically limited by thermodynamic efficiency, so by Carnot efficiency, which is also telling us another interesting point. If we want to improve the efficiency, we of course have to improve the ratio of the temperatures because of Carnot limits, and that means we have to operate as high temperature as possible for our walls, materials, and blanket, and that is another additional requirements that we may have. That is something we have to still do R&D on.
Okay. The next question is, how impactful is the new research using small 3D magnetic perturbations in plasma confinement?
I'm not sure what the question refers to.
So, Professor, I'll let the participant rephrase the question, and we can circle back.
Okay.
We can take the next one. So the next question wants to please tell us more about NBI of TAE technology and avalanche fusion technology. What is new going on in there?
Okay, and about NBI of TAE technology.
Again, the same thing. I would ask the participant to please
I'm not
rephrase the
too
question.
sure.
Yeah, I'll take the next one. We can circle back if there is time, always. So which areas in physics and physics plus artificial intelligence, let's say, has to be more focused or has to come together to reach Q equals to 5 in your mind?
Very interesting. So this is related to my brief discussion on the burning plasma regime. You have to really make sure that once you're in the burning plasma, you don't have big surprises compared to the present regimes that we have, because in the burning plasma, you have a dominance of the alpha particle heating, and therefore the alpha particles have to be maintained stable inside the plasma. Can you optimize the control using AI? Yes, I think we have to move in that direction. It's a very good question, a very good, let's say, proposal to some extent. I hope some of you guys can go into that direction, because if you use AI to combine the sort of conventional control with the physics knowledge that we have, you can be very effective. We have demonstrated that, not so much for burning plasma regime, but for the plasma shape in our own tokamak in Lausanne, working with DeepMind, which is, the AI company of Google. For the first time, we demonstrated that using AI, you can control the tokamak plasma, and that is very, very promising. But we have done it by injecting into the AI algorithm the knowledge of plasma physics for control that we had. And so this combination was really, if you like, the game changer for that. So I think this applies also to the 𝘂=5 obtention and stable control. So it's certainly an avenue for research that I would suggest that some of you follow.
I can put in the chat box your 2022, I think it was a science paper, right? With DeepMind. Yeah. And it's a very interesting read. I'll put it in the chat box so people can click on the link and read it. It's a kind of a must-read paper that. So another question is, where Europe is now on the demo reactor, and how it landed on the 300 megawatt and 2 hours numbers.
Okay, we are not developing demo yet. But there was a pre-design. There were discussions also of a first step of it in terms of evaluating neutron source. So the decision is not taken yet. Why did we end up with 300 megawatt and 2 hours? Because the question is how do you provide a demonstration at the level that's sufficient? And so we discussed with the facilities, and for them, having a cycle of 2 hours was something that would be convincing, and the level of power had to be of that size in order, again, to be tested, to be injected in the grid, and to be tested in a realistic condition for commercialization. That's what we understood from our discussion with the facilities providing energy in Europe.
Okay, maybe one last question, Professor.
Yeah.
So it says, why fusion reactors cannot be simply, let's say, pulsed for, let's say, 1 minute on and 1 minute off, considering the heat diffusion time in the blanket and moment of inertia of the turbine?
They can. I mean, if it could be, well, 1 minute off is a bit difficult because probably you need to take a little bit more time to recharge your transformer and so on. But we're talking about several minutes. The longer we on, the better. But it's true that I think the inertia of the system will allow even a tokamak to be providing basically steady state energy out in a plant that it's designed for that, of course.
Okay. Well, Professor, I can see the level of excitement from the number of questions, but we have to restrict because of time constraints. And you said you had a hard, like a deadline and a meeting, something at 3:15 of Central European time. So I'll thank you very much for this truly enriching and insightful lecture. Before we close, I'm pleased to share that Dr. Rajesh, I think he was in the panel and he briefly left from Princeton, has graciously agreed to return for another session, which is in the middle of February. We will share the circular and the notification with all of you. I thank all of you again for your participation, your engagement, to all our esteemed panelists for their time, and especially you, Professor Fasoli, for your very generous contribution to this masterclass series. Thank you very much.
It was my pleasure. My pleasure, and it was great seeing some of
yes.
the friends online as well.
Yeah, thank you, Ambrogio. It was great to listen to you.